Living organisms are basically a bunch of carbon compounds working together. The number of known molecules that contain carbon, either naturally occurring ones or man-made ones, exceeds all other known molecules of all the other elements put together. I think it has carbon has around 3 times more compounds than all the other elements of the periodic table put together. So even if it doesn't sound like very abundant, it's actually fundamental. And the reason why it's so fundamental to us is because it's essential to life. Most molecules in living organisms are based on a carbon skeleton. And that is what organic chemistry is. The chemistry of carbon and its compound. The chemistry of carbon and carbon combined with some other key elements, mostly hydrogen, but also oxygen, nitrogen, phosphorus, and sulfur. We often say that carbon and hydrogen are the building blocks of life. So how do you make sense of organic chemistry, of carbon compounds? How can you make sense of the compounds of an element that has 3 times more compounds than all the other elements of the periodic table put together? And we're talking about the other 117 elements of the periodic table. Well, we don't study the organic compounds one by one or even a few together. We study them in families. Families that possess certain key characteristics, things that have in common that make them behave physically and chemically in a similar way. And those families are divided by functional groups. Functional groups is a group of atoms that are repeated over and over again in organic compounds. And quite often those functional groups or a molecule does not contain only one functional group. It possesses several of them, and we're going to be looking at many examples over the next few slides. Understanding what those functional groups do, what they are, and what characteristics they have, help us, even if we have never seen a molecule before, help us have some educated guesses about what that molecule may or may not be able to do. So for example, if I look at the molecule on the left of the slide, that's histidine. It's an amino acid. And I can quickly see that it has several carbons, it also has nitrogens, and it has oxygens, a couple of oxygens. So if I spot here this part, this is a functional group called carboxylic acid. And carboxylic acid are weak acids. So because I know it's a carboxylic acid, I know that that molecule is going to be able to behave as an acid, as a weak acid. On the other hand, I also spot here, I've got a nitrogen here and I've got a nitrogen here. Those are amines. And amines are bases. They are weak bases. So I know that that compound will be able to behave as a base. So it will be able to behave as an acid because it has an acidic functional group, and as a base because it has the basic functional groups, especially this one. And in reality, it's true, histidine is an amino acid, and it has a basic side and a more acidic side. If I look at the molecule on the right-hand side as epinephrine, that's a hormone, I spot this structure, these 6 carbons in a hexagon with these 3 alternated double bonds. That's a benzene ring, that's an aromatic ring, and that's a type of functional group that's going to give a lot of stability to the molecule. And I know that because I know about the chemistry of benzene. And benzene is not very soluble in water, actually it's not soluble in water at all. However, I spot other groups in my molecule, like for example these ones, OH, OH, that's hydroxyl groups, those are alcohols. And hydroxyl groups, alcohols, are soluble in water. So actually that might help the solubility of that molecule because those OHs, those hydroxyl groups, can interact with water. And I also spot the nitrogen that we had before, an amino group. So that compound is going to be able to behave like a weak base. So just without knowing that much about this compound, I can already have some educated guesses about how it's going to behave, the physical properties and also the chemical properties, which I particularly care about because I'm a chemist. Just because I know I know things about the functional groups it contains. Okay, I cleared the slide so it was not so cluttered with all the stuff, so you have more space to look at the compound here. I will highlight it again. So I've got the oxygen in the middle, and the oxygen is the oxygen. I need to, it's there, so it's part of the molecule. And I see my oxygen has lines coming of it. So again, when there is a corner, I put a carbon. When it's the end of the line, I put a carbon. So from this side, when there is a line, the end of the line, I put a carbon. There's a corner there. So when then there is a corner, I put a carbon. When there's the end of the line, I put a carbon. So I have mapped out the structure with the carbons and the oxygen I already had. So that's the carbon skeleton. And now I just need to add the hydrogens. Well, again, carbon needs 4 bonds. So the hydrogens in the ends will have 3 bonds to hydrogens each. And the 4th one to the carbon. And the 2 carbons next to the oxygen, because they already have 2 bonds, one to the oxygen and one to another carbon, will only have 2 hydrogens each. And if I want to draw that molecule in a slightly more condensed structure, I will write CH3, CH2O, CH2, CH3. And that's diethyl ether, or what we typically call ether. So even if I write again those H3 and those H2 together, I know that the bonds are between the hydrogens and the carbon they are next to it. And even if I randomly put a line in between a bunch of hydrogens and a carbon, I know that those lines represent bonds between carbons or bonds between the carbon and the oxygen. So here's how to represent the same compound. Octane is an alkane that has 8 carbon atoms in 3 different ways. You can give the full structural formula, so all the carbons, all the hydrogens, and all the bonds being perfectly visible. You can write what we call the condensed structural formula, in which you condense the bonds of the carbon and the hydrogens, and you don't write a carbon with the hydrogens attached to them. Yes, you put the H3, and this is the same. You can even condense it even more. If you think about it, this compound has a CH3s, a bunch of CH2s, and another CH3. And if I count the CH3, I have 1, 2, 3, 4, 5, 6. So you will also see in some books or some papers that you will give you this structure here, that when you have a repeated unit, you put them in brackets and put, in a subscript how many repeated units you have of that particular, in this case, CH2. Or the most common structure is the line segment structural formula, in which you're only drawing the lines, and because in this case the only atoms you have in this structure of octane are carbons and hydrogens, you just get the lines. You don't have any other atom visible. And the last thing that you will see in many cases in an organic formula. Sometimes you will see a formula. This is, for example, the formula of benzene. And maybe we'll have something like this here, R. And you will think, what's that? R. There's no element called R. Well, R is what I like to think of the rest of the molecule. It's a trick that we often use in organic chemistry when we want to draw molecules, but we're only interested in a particular functional group, in a particular aspect of the molecule. So the rest of the molecule is there, we know it's there, but it's not going to react, it's not going to act. We are not interested in that particular moment in that part of the molecule. For example, let's look at a molecule of histidine that I showed in a previous slide. Imagine that I was interested in the behavior of histidine as an acid. This is the acidic group. This is a carboxylic acid group. So if I were interested in the behavior of histidine behaving as an acid, let's say, how does it interact with water as an acid? How does it interact with a base? Well, I will draw this bit because I care about this bit. This bit is important. It's the one that is going to act as an acid, specifically this hydrogen. And then there's the rest of the molecule. And I don't care about the rest of the molecule. It's just, it is there. It's not that this carbon is not attached to something. It's attached to everything that is on the left, but we don't care about it. However, imagine I was interested in the behavior of histidine as a base. So I was interested in seeing how histidine reacts with acids. So if I look, then I will be interested specifically in that NH2, in that an amino group. So what would I write? Well, I will write this CH, NH2, and then there are two things coming off of my CHNO2, NH2, but I don't care about them. I mean, I care because I know that carbon needs 4 bonds, so they need to be there, but I don't care what they are. So I will call them R. And because they are different, you know, this part of the molecule is different to this part of the molecule. So I cannot use the same letters. I would probably write R and R prime, or R1 and R2. You will see many times, you will see R1 and R2, R3, or R and R prime, or R double prime. I will make sure that my reader knows that these two R's are different. They represent different atoms, but that they are not important in this case because I am interested specifically in this part of the molecule.